Atoms break in three classical ways. Alpha decay spits out a helium nucleus. Beta decay flips a neutron into a proton, or vice versa. Gamma decay just sheds a photon. Rutherford named alpha and beta in 1899. Villard added gamma in 1900. Every entry in the chart of nuclides outside the valley of stability does one of these. Alpha decay. A heavy nucleus tunnels out a tightly bound cluster of 2 protons and 2 neutrons, a helium-4 nucleus. The parent loses 4 units of mass number and 2 units of atomic number. Kinetic energy of the emitted alpha sits around 4 to 7 million electron volts. Concrete example: uranium-238 decays to thorium-234 plus an alpha. Q value 4.27 megaelectron volts, half-life 4.5 billion years. This is the head of the uranium decay series, the chain that ends in stable lead. Beta minus decay. Inside the nucleus, a neutron turns into a proton via the weak interaction. Out come an electron and an antineutrino. Mass number stays the same. Atomic number jumps up by 1. The electron spectrum is continuous because 3 bodies share the energy. Carbon, 14 beta minus decays to nitrogen-14 with a half-life of 5,700 years. Cosmic rays make C14 in the upper atmosphere. Living things absorb it. Once death stops the intake, the carbon-14 clock starts. Radiocarbon dating works back about 50,000 years. Beta plus decay does the reverse. A proton becomes a neutron and emits a positron plus a neutrino. The positron annihilates with a nearby electron, producing 2 back-to-back 511 keV gamma rays. PET scanners detect those coincident pairs. That's how fluorine-18 FDG lights up tumors. Gamma decay. The nucleus already has the right number of protons and neutrons, but it's in an excited energy state. It relaxes by emitting a high-energy photon, typically 0.1 to 3 megaelectron volts. No change to atomic number, no change to mass number. Often follows alpha or beta as a cascade. Penetration matters for safety. A sheet of paper stops alpha. A few millimeters of aluminum stops beta. Gamma needs centimeters of lead. The reason? Alphas are heavy and charged, betas are light and charged, gammas are uncharged photons that only attenuate exponentially. Every decay obeys the same statistical law. The number of nuclei left after time t equals n-0 times e to the minus lambda t. The half-life is the time for half to decay. Across all radioactive isotopes, half-lives span more than 60 orders of magnitude, from femtoseconds to billions of years. Applications everywhere. PET imaging localizes tumors via positron annihilation. Radiocarbon dates archaeological finds. Smoke detectors use americium-241 alphas. Cobalt-60 gammas sterilize medical equipment and treat deep tumors. The same 3 radiations that once puzzled Rutherford now save lives and date civilizations.